The universe should be full of life, but it's silent. And every explanation is disturbing. The first radio silence evidence. The Milky Way is not small in any human sense. It holds between 100 and 400 billion stars, and around those stars, we now know planets are not rare at all. In fact, modern astronomy has shown that planets are the rule, not the exception, and among those billions of planets, a significant number sit in the so-called habitable zone, where liquid water could exist and chemistry could move toward life. The galaxy itself is about 13.6 billion years old, which means there has been more than enough time for life to appear, evolve, and spread multiple times over. Even if intelligent life is extremely rare, even if it requires a long chain of unlikely steps, the sheer scale of time and space makes the absence of any confirmed signal feel out of place. This is where the paradox begins to tighten, because the expectation is not based on imagination, but on scale. If even a small fraction of planets developed intelligent life, and even smaller fractions developed technology, the galaxy should not feel silent. Yet when we look, when we listen, when we scan the sky across different frequencies, the result is the same repeated silence. No confirmed transmissions, no structured signals, no undeniable artifacts, just background noise that behaves exactly as expected from natural sources. This silence is not from lack of effort. For decades, radio telescopes have been pointed outward in structured searches designed to pick out narrowband signals that nature does not usually produce. The assumption is simple. If another civilization is using radio in any similar way we once did, there should be traces. This expectation became stronger during the early era of radio astronomy, when scientists first realized that Earth itself was unintentionally broadcasting signals into space. That realization led to a shift from passive listening to active searching, and one of the earliest organized attempts came in 1960 with Project Ozma. This was not a large mission by modern standards, but it was historic in purpose. Frank Drake pointed a radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened carefully for artificial signals. The idea was straightforward. If even one nearby star system hosted a civilization even slightly more advanced than ours, there might be detectable radio emissions leaking into space. What came back was silence. No repeating patterns, no narrow frequency spikes, nothing that could be separated from natural cosmic noise. At the time, this was not seen as a failure, but as a first data point. Still, it carried weight because it was the first time humans had intentionally searched nearby star systems with the expectation of finding something artificial. The absence of a signal did not prove anything on its own, but it began to set a pattern that would repeat across later surveys. The more the sky was observed, the more refined the equipment became, and the more regions were scanned, the same result kept appearing. Empty sky after empty sky. Not because space is empty in a physical sense, but because nothing clearly artificial has ever been confirmed. As radio astronomy expanded, this silence became harder to ignore, especially when combined with what we now understand about planetary formation. Stars like the Sun are not rare. Planets like Earth, at least in size and orbital distance, are not rare either. Even complex chemistry appears to form easily under the right conditions. This creates a tension in expectation because the building blocks of life do not appear to be the limiting factor. The paradox is not about whether life can exist, but whether it should have appeared often enough to leave visible traces. And yet, even after decades of scanning, including large structured efforts that monitor thousands of stars across different frequencies, no confirmed extraterrestrial intelligence has been detected. What makes this more striking is that Earth's own radio leakage has already been traveling outward for about a century. That means any civilization within roughly 100 light years that had similar technology and was actively listening in the right way could, in theory, detect us. That distance contains thousands of star systems, if the galaxy were filled with active civilizations using similar communication methods, overlap in detection windows should be likely. Instead, the searchers have returned nothing that clearly stands apart from natural astrophysical phenomena. This is where the problem shifts from being just about numbers to something deeper about timing, behavior, or even the nature of intelligence itself. Project Ozma becomes important not because it found something, but because it defined the beginning of an expectation. It showed that we are capable of listening, that we can aim instruments at nearby stars and search for patterns that should not exist naturally. It also showed that the immediate neighbourhood, at least the part we first examined, does not offer easy answers. The silence was not dramatic, it was clean and consistent, and that consistency is what makes it scientifically uncomfortable. Because in a galaxy with this many stars, with this much time, and with planets forming everywhere we look, a completely quiet result starts to feel less like absence of search and more like absence of signal itself. And that is where the core scientific problem stays fixed. Not in the idea that life is impossible, not even in the idea that intelligence is rare, but in the repeated failure to detect anything that confirms we are not alone. The instruments have improved, the surveys have expanded, the understanding of planets has grown, yet the outcome remains unchanged. Space does not answer back in any way we recognize, and every new layer of observation only deepens the same question that started it all. Because the more carefully we listen, the more the silence holds its shape. The Drake equation, expanding the unknown. The Drake equation. Drake equation was created as a way to turn the Fermi paradox from a vague question into something structured, something that could actually be discussed in numbers instead of guesses. Frank Drake introduced it in 1961, not as a final answer, but as a framework that breaks the problem of alien civilizations into separate parts that can be studied one by one. Instead of asking a single, overwhelming question like, how many civilizations exist in the galaxy, it separates the problem into steps that must all happen for a communicating civilization to exist. Each step depends on a different stage of cosmic and biological development, and each one carries its own uncertainty. When these steps are multiplied together, the result can swing from a galaxy filled with life to a galaxy almost completely empty, depending on how each unknown is valued. The first factor looks at how many stars form in the Milky Way each year. This part is relatively well measured compared to the others, because astronomers can observe star formation in real time across different regions of the galaxy. Stars are constantly being born in giant clouds of gas and dust, and although the exact rate changes over time, the general picture is stable enough that it does not create extreme uncertainty. The next step, however, introduces the first major shift in uncertainty, because it asks what fraction of those stars actually have planets. At the time the equation was first introduced, this was still unknown. But modern astronomy has now shown through missions like Kepler that planets are extremely common. Many stars have multiple planets, and planetary systems appear to be a standard outcome of star formation rather than a rare event. This changes the starting conditions of the equation dramatically, because it removes one of the early bottlenecks that might have limited life. The next variables begin to move into territory where direct measurement becomes harder. One of the key questions is how many of those planets are capable of supporting life. This is not just about being the right distance from a star, but also about having stable conditions over long periods of time. Liquid water, stable atmospheres, and protection from extreme radiation all matter, but these factors are difficult to evaluate across distant systems. Even within our own galaxy, we only have one confirmed example of a life-bearing planet, which means any estimate beyond Earth involves a large degree of uncertainty. This single data point problem becomes even more intense when the equation moves from habitability to actual life formation, because the step from chemistry to biology is still not fully understood. The equation then moves into one of the most uncertain transitions in science, the fraction of habitable planets where life actually begins. This is where uncertainty expands sharply, because even though organic molecules are known to form in space and on planets, the step from chemistry to self-replicating life has never been observed directly outside Earth. Some models assume this step is easy and happens frequently wherever conditions allow, while others suggest it could be extremely rare, requiring a sequence of conditions that are unlikely to align. This single variable can shift the outcome of the entire equation by many orders of magnitude, because if life is rare at this stage, then even a galaxy full of habitable planets could still remain mostly lifeless. After life appears, the equation introduces the probability that intelligent life evolves. This is another major uncertainty, because evolution does not have a fixed direction. On Earth, intelligence emerged after billions of years of evolution, but there is no guarantee that this outcome is common. Many species have existed for far longer without developing anything close to technological intelligence. This means that even if life itself is common, intelligence might still be a rare outcome, dependent on long chains of environmental stability and evolutionary pressure that do not always repeat elsewhere. This variable introduces the possibility that complex life exists widely, but technological civilizations are still extremely rare. Then comes one of the most critical and often overlooked parts of the equation: the fraction of civilizations that develop detectable communication technology. Even if intelligent life exists, it does not automatically mean it produces signals we can detect. Civilizations may never develop radio technology, or they may quickly move beyond it into forms of communication that do not leak into space. On Earth, radio emissions have only existed for a short window of time, and already there is movement toward fiber optics, encrypted networks, and communication systems that produce far less leakage. This suggests that the detectable phase of a civilization may be brief, which directly affects the chances of overlap between their signals and our observations. The final factor in the equation is the average lifetime of a communicating civilization. This variable is where the equation becomes especially sensitive, because even small changes have large effects on the final result. If civilizations tend to destroy themselves shortly after developing technology, or if they naturally transition into silent forms of existence, then the window for detection becomes extremely narrow. On the other hand, if civilizations can survive and maintain detectable signals for millions of years, then even a small number of civilizations could fill the galaxy with overlapping signals. This single variable controls whether the galaxy should feel active or silent at any given moment. What makes the Drake equation powerful is not that it gives a fixed answer, but that it shows how fragile every assumption is. Each term depends on knowledge that is still incomplete, and each uncertainty multiplies the others. A small change in any one factor can shift the final estimate from millions of civilizations to almost none. This is why the equation does not resolve the Fermi paradox, but instead expands it. It shows that the silence we observe is not necessarily a mystery with one cause, but a result that could emerge from many different combinations of conditions. Some combinations suggest a galaxy filled with life that we simply cannot detect. Others suggest a universe where intelligent life is rare enough that we may be alone in a practical sense, even if not in a strict mathematical one. The rare Earth hypothesis. Complex life is a statistical accident. The rare Earth hypothesis. Rare. Earth hypothesis starts from a simple but strict idea. Life might not be rare in general, but complex life like animals, plants, and especially intelligent life could depend on a very specific set of conditions that do not often come together in the same place. It does not argue that planets are rare, because we now know planets are common across the galaxy, but it focuses on the idea that a planet being Earth-like is far more demanding than just being rocky and in the right temperature range. The hypothesis builds on the observation that Earth is not just a habitable planet in a basic sense, but a system where many separate stability factors have aligned for billions of years without breaking down. One of the first conditions often highlighted is the stability of the host star. Earth orbits a G-type main sequence star, the Sun, which has remained relatively stable over long time scales. This stability matters because sudden shifts in radiation output or stellar flares can strip atmospheres or disrupt planetary climates. Many stars in the galaxy are smaller red dwarfs, which are long-lived but often highly active in their early stages, producing intense flares that could make nearby planets hostile to stable biological development. If a planet sits too close to avoid freezing, it risks radiation exposure, and if it moves farther out, it risks losing heat. This balance problem suggests that not every star provides a stable environment for long-term biological evolution, even if planets are present. Another key factor is the presence of a large moon, like Earth's moon. The moon does more than create tides. It stabilizes Earth's axial tilt over long periods. Without this stabilizing effect, a planet's tilt could shift dramatically over time, leading to extreme and unpredictable climate changes. On a planet without this stability, ice ages and heat extremes could occur in irregular cycles that prevent complex ecosystems from developing consistently. The formation of a large moon is itself not guaranteed, because it likely requires a rare giant impact event during the early formation of a planet. That means even if Earth-like planets form, only a fraction may have the additional stabilizing influence of a large satellite. The hypothesis also emphasizes the importance of a magnetic field, which is generated by movement in a planet's molten core. This field acts as a shield against solar wind and cosmic radiation, helping preserve a planet's atmosphere over billions of years. Without it, a planet can gradually lose its atmosphere, as may have happened to Mars, which once had liquid water but now has a thin atmosphere and a cold, dry surface. A magnetic field is not guaranteed for every rocky planet because it depends on internal heat, rotation rate, and core composition. If any of these factors differ, the protective shield may weaken or never form properly, exposing the surface to radiation that makes long-term complex life far more difficult. Plate tectonics is another factor that plays a quiet but critical role. On Earth, tectonic activity recycles carbon through the crust and mantle, helping regulate atmospheric carbon dioxide over long time scales. This creates a kind of planetary thermostat that keeps climate within a range suitable for liquid water and biological activity. Without this cycle, a planet might experience runaway greenhouse conditions or permanent freezing. However, plate tectonics is not universal among rocky planets. It depends on internal heat, crust composition, and water presence, and even small differences in these conditions can stop tectonic movement entirely. That means a planet could be habitable in a short-term sense, but unstable over the millions or billions of years needed for complex life to evolve. Long-term climate stability ties all of these factors together. Complex life does not just require a moment of habitability, it requires consistency across deep time. Life on Earth took billions of years to move from simple single-celled organisms to complex multicellular systems, and even longer to produce technological intelligence. If a planet's environment resets too often due to orbital instability, stellar variation, atmospheric loss, or geological collapse, evolution may never have enough uninterrupted time to reach advanced stages. This makes time itself a critical resource, not just conditions at any single moment. What makes the rare Earth hypothesis powerful is not any single requirement, but the combination of all of them working together. A stable star alone is not enough if the planet lacks a protective magnetic field. A habitable zone orbit is not enough if climate cycles are too extreme. A planet with water is not enough if it cannot maintain that water over billions of years. Each factor on its own might be common, but the hypothesis suggests that the full set acting together could be rare enough to drastically reduce the number of worlds that ever develop complex life. This changes the way the silence of the galaxy is interpreted. Instead of assuming that life should naturally spread everywhere it can, the rare Earth perspective suggests that Earth may represent a very specific outcome of many low probability conditions stacking together in the same place over the same long time scale. In that case, the absence of detectable civilizations is not surprising, because the chain leading from basic chemistry to complex intelligence may not be a frequent outcome at all, even in a galaxy filled with planets that look similar at first glance. The Great Filter, Civilization Bottleneck Theory. The Great Filter is one of the most unsettling ways scientists try to explain the silence behind the Fermi paradox, because it does not try to soften the contradiction between expectation and observation. It instead tries to locate where the process of life most likely fails. The idea is simple in structure, but heavy in implication. If the galaxy is large, old, and filled with billions of potentially habitable planets, then something must be stopping life from consistently reaching the stage of advanced, spacefaring civilization. That something is not a single event, but a barrier somewhere along the long chain from chemistry to intelligence to interstellar expansion. The key issue is that this barrier could be anywhere along that chain, and we do not know whether it is already behind us or still waiting ahead. To understand why this idea exists at all, it helps to look at the full sequence of steps required for a technological civilization like ours to emerge. First, you need stable planets with the right chemical ingredients. Then you need the formation of organic molecules, followed by the emergence of self-replicating systems we call life. After that, life must evolve into complex multicellular organisms, then into intelligent species capable of manipulating tools, and finally into civilizations capable of building technology that can leave their planet and communicate across interstellar distances. Each of these steps is not guaranteed. Each one depends on physical, chemical, and environmental conditions that may or may not repeat elsewhere. The Great Filter is the idea that at least one of these steps is so unlikely that it effectively limits how many civilizations can exist in the galaxy at any given time. What makes the concept so important is not just that it explains silence, but that it forces a directional question. If there is a filter, where is it located in the sequence? Is it something that most planets never pass, like the origin of life itself? Or is it something that most civilizations fail after reaching a certain level of technology? The answer to this determines whether humanity has already passed the hardest part, or whether we are approaching it without realizing it. One possible version of the Great Filter is placed very early in the chain, near the origin of life. On Earth, life appeared relatively early in geological history once conditions stabilized. But that single example is not enough to conclude that abiogenesis is easy. We have no second example to compare it with. If the transition from non-living chemistry to self-replicating biology is extremely rare, then most planets, even those with water and organic molecules, may remain permanently lifeless. In that scenario, Earth would be an exception that passed through an extremely unlikely step early in its history. The implication is that the galaxy could be filled with suitable environments that never actually crossed the threshold into life, making advanced civilizations almost non-existent, not because intelligence is rare, but because biology itself is rare. Another early possibility is the transition from simple single-celled life to complex multicellular organisms. For most of Earth's history, life remained microbial. Complex multicellular life only appeared after billions of years of relatively stable conditions. If that transition is not a natural outcome of evolution, but a rare evolutionary accident, then most planets could remain stuck at the microbial level indefinitely. Microbial life could be widespread in the universe, even common across many star systems, but it would produce no technology, no communication, and no detectable signals. This version of the filter is still early in the sequence, but it changes the interpretation of silence completely. It suggests the galaxy might be alive in a microbial sense, but invisible in every way that matters for interstellar detection. A further step in the sequence is the development of intelligence itself. On Earth, intelligence evolved in a specific lineage of life, but there is no guarantee that evolution naturally produces intelligence frequently. Evolution is driven by survival pressure, not by any goal toward intelligence or technology. Many species thrive for millions of years without developing advanced cognition. If intelligence is a rare adaptation that only appears under very specific ecological pressures, then most planets with complex life might still never produce technological beings. In that case, life could be abundant, but civilizations could remain extremely rare. Even if intelligence does arise, another potential filter appears in the transition to technological capability. Intelligence alone does not guarantee tool use, industrial development, or scientific understanding. Many intelligent species on Earth show different forms of cognition, but only one developed technology capable of leaving the planet. This raises the possibility that the jump from intelligence to technological civilization is itself a rare step, dependent on environmental stability, physical manipulation ability, and long-term cognitive development. If this step is rare, then even intelligent life could exist widely without ever becoming detectable in space. The most disturbing version of the Great Filter, however, is not in the past, but in the future. If humanity has already passed all the difficult early steps, then the filter may lie ahead, meaning that most civilizations reach a certain level of technological development and then fail to continue. This introduces a completely different interpretation of the silence in the sky. Instead of asking why we do not see others, the question becomes whether those who once existed managed to survive long enough to become visible at a galactic scale. If civilizations tend to self-destruct after developing powerful technologies, then the absence of signals is not evidence of rarity in life, but evidence of a repeated pattern of failure after intelligence emerges. This forward-looking version of the filter includes several possible mechanisms. One is internal collapse caused by technological escalation, where a civilization develops tools powerful enough to destabilize its own environment faster than it can adapt. Another is environmental exhaustion, where planetary resources are consumed faster than they can regenerate, leading to collapse before interstellar expansion becomes possible. There is also the possibility of uncontrollable technological systems, where artificial intelligence or automated infrastructure evolves in ways that outpace human control. Each of these scenarios does not require external threats from space. They can occur entirely within a single planet's technological evolution. The reason the Great Filter is so difficult to resolve is that we only have one data point, Earth. We do not know which steps were easy and which were unlikely, because we only observe a single successful outcome. Life appeared here, intelligence appeared here, and technology appeared here. But that does not tell us how often these events happen elsewhere. It only tells us that they are possible. This limitation means that every step in the sequence remains uncertain, and the filter could be hidden anywhere along it. This uncertainty creates a split interpretation of the same silence we observe in the galaxy. If the filter is behind us, then humanity is an extremely rare success story in a universe where most planets never reach this stage. That would mean the future is open, but the past was extremely unlikely. If the filter is ahead of us, then the galaxy may have produced many civilizations that all reached a similar level of development, but none survived long enough to become visible on interstellar timescales. In that case, the silence is not empty space, but a record of repeated endings. What makes the Great Filter concept so central to discussions of the Fermi paradox is that it does not rely on imagination or speculative physics. It is grounded in a simple statistical problem, when multiple low probability steps are required for a final outcome. The overall probability becomes extremely sensitive to any single step. Even if most steps are likely, one rare step can dominate the entire process. The question is not whether life is possible, but whether the chain from chemistry to interstellar civilization contains a breakpoint so strong that it shapes the entire galaxy's visible history. The "we are early" solution, cosmic timing bias. The "we are early" explanation for the Fermi paradox starts with a simple but often overlooked fact about the universe. It has not always been chemically ready for life like ours. Even though the universe is 13.8 billion years old, the ingredients needed for rocky planets and biology did not exist in large amounts at the beginning. The early universe was mostly hydrogen and helium formed after the Big Bang, and it took long generations of stars living and dying before heavier elements like carbon, oxygen, silicon, and iron became widespread. These elements are not optional details for life as we know it. They are the basic building blocks for chemistry, geology, atmospheres, and biological systems. Without them, planets like Earth cannot form in the first place. This is where the timing argument begins to shift the way we interpret the silence in the galaxy. In the earliest cosmic epochs, the first stars were massive, short-lived, and unstable compared to stars like the Sun. They burned fast and died in violent supernovae, spreading heavier elements into space, but not leaving behind calm, stable environments long enough for complex planetary systems to develop. The universe during that time was chemically active, but not structurally stable in the way needed for long-term biology. This means that even though the universe was already old in a numerical sense, it was still young in terms of complexity. The raw materials for life were still being built. As generations of stars continued to form and die, each cycle enriched the galaxy with more heavy elements. Carbon and oxygen became more common, rocky planets began to appear more frequently, and stable star systems like our own became possible. Our Sun formed about 4.6 billion years ago, relatively late compared to the age of the universe, in a region of the Milky Way that had already been enriched by previous stellar generations. This timing matters because it suggests that Earth did not form in the early chaotic phase of the galaxy, but in a later stage where conditions had stabilized enough for long-term chemistry and biology to become possible. The "we are early" argument takes this idea further by suggesting that civilizations like ours may only begin to appear once the galaxy reaches a certain level of chemical maturity. If heavy elements were rare or unevenly distributed in earlier eras, then Earth-like planets would also have been rare or non-existent during those periods. Even if life could theoretically form earlier, the number of suitable environments may have been too low for civilizations to emerge in significant numbers. In that case, the galaxy would not have had enough time in its early history to produce many observers capable of developing technology and sending signals. This perspective changes the meaning of silence in a subtle but important way. Instead of assuming that civilizations should already have filled the galaxy if they exist, it suggests that we might be among the first generation of civilizations that are emerging at a time when the galaxy has finally become suitable. In this view, the absence of detected signals is not because civilizations have failed or disappeared, but because the process of civilization emergence itself is only now reaching a stage where it becomes statistically likely. The galaxy may not be empty, it may simply be in an early phase of producing technological intelligence. A key part of this argument comes from how star formation and element production evolved over time. Early stars were metal poor, meaning they lacked the heavier elements astronomers refer to as metals. These metals are essential for forming rocky planets with complex geology and chemistry. Without them, planetary systems would either not form or would consist mainly of gas giants or unstable bodies unsuitable for long-term surface chemistry. As successive star generations enriched the interstellar medium, the probability of forming Earth-like planets increased. This means that the conditions for life have been improving over time, not remaining constant. From this perspective, the Milky Way is not a static environment where civilizations should appear evenly across time, but a developing system that gradually becomes more capable of producing life-supporting planets. If that development is still ongoing, then the earliest possible civilizations might only now be emerging in different parts of the galaxy. This introduces a strong timing bias into the Fermi paradox, because our observation window is extremely narrow compared to cosmic timescales. We are looking at the galaxy at one moment in time, assuming it should already be filled with advanced civilizations, but that assumption may not account for how long it actually takes for the necessary chemical and planetary conditions to become widespread. Another important factor in this idea is the delay between planet formation and biological evolution. Even on Earth, life took hundreds of millions of years to stabilize, and complex life took billions of years to emerge. Intelligence and technology appeared even later in that timeline. If this pattern is not unusual, then even after Earth-like planets become common, there is still a long delay before civilizations capable of detection appear. This delay creates a natural lag between the formation of suitable planets and the emergence of observable technological activity. The "we are early" solution also implies that the galaxy could still be in a transitional phase, where many planets capable of developing life have only recently formed. In this scenario, life itself might be common, but technological civilizations could still be rare simply because not enough time has passed for evolution to reach that stage on many worlds. The universe does not produce intelligence instantly once conditions are right. It requires long periods of stability, survival pressure, and environmental consistency. If those stable conditions have only become widespread in the last few billion years, then most civilizations in the galaxy might not yet have had enough time to appear. This leads to a different interpretation of the silence we observe. Instead of treating it as evidence of absence, it becomes a reflection of cosmic timing. We are not necessarily early in the sense of being unique or first, but early in the sense that the conditions for widespread intelligence may still be spreading across the galaxy. The signals we expect to detect from other civilizations may not exist yet, not because they are impossible, but because the universe has only recently reached the stage where they can begin to form in large numbers. What makes this explanation particularly important in the broader set of Fermi paradox solutions is that it does not require rare physics, rare biology, or repeated civilization failure. It only requires time. If the build-up of heavy elements, stable planetary systems, and long-term habitable environments is a gradual process, then the emergence of civilizations is also likely to be gradual. In that case, the silence is not permanent, but temporal, tied to the fact that we are observing the galaxy before its full potential for life has been realized. From this angle, the universe is not necessarily empty of life, and it is not necessarily full of civilizations that we are failing to detect. Instead, it may simply be in an early stage of producing them, where the first waves of intelligent observers are only now beginning to appear. The galaxy, in this interpretation, is not a finished system, but one still in the process of becoming capable of hosting widespread intelligence, and our observation happens at a moment when that process may still be unfolding across vast regions of space. The self-destruction hypothesis. Technological extinction. The self-destruction hypothesis begins with a blunt interpretation of the Fermi paradox. The galaxy may not be silent because life is rare, but because technological life does not last long enough to become visible across interstellar distances. In this view, civilizations may appear, develop rapidly once they reach a certain scientific threshold, and then collapse or disappear before they ever spread beyond their home planet or produce long-lasting signals that could be detected elsewhere. The key idea is not that intelligence is unlikely to arise, but that intelligence combined with advanced technology may be unstable over time. On Earth, the transition into technological capability has been extremely fast compared to biological evolution. For most of human history, progress was slow and localized, but within a very short period in cosmic terms, the development of industrial systems, global communication, nuclear energy, and artificial intelligence has changed the scale of human impact entirely. This speed matters in the hypothesis because it suggests that once a civilization reaches a certain level of technological control over energy and systems, its internal risks increase faster than its ability to manage them. The result is a narrow window between becoming detectable and becoming unstable. One of the earliest and most discussed mechanisms for self-destruction is large-scale nuclear conflict. Once a civilization discovers how to harness nuclear energy, it also gains the ability to produce weapons with destructive capacity far beyond anything in its natural environment. The concern is not limited to direct destruction alone, but also includes long-term environmental effects that could disrupt agriculture, atmospheric stability, and population systems. Even a limited nuclear exchange could trigger cascading effects on food production and climate systems, creating conditions that a global civilization may struggle to recover from. In the context of the Fermi paradox, if many civilizations reach this stage, even a small probability of self-inflicted collapse could significantly reduce the number that survive long enough to expand beyond their planets. Another possible pathway is engineered biological systems. As biological science advances, civilizations gain the ability to modify organisms at the genetic level. This creates both medical and agricultural benefits, but it also introduces the risk of engineered pathogens that could spread beyond control. Unlike natural diseases, engineered biological agents could be designed for high transmission efficiency or resistance to treatment systems, making containment difficult once released. A civilization that becomes globally interconnected through trade and communication networks may also become more vulnerable to rapid biological spread, where localized outbreaks can escalate into global system stress. Climate collapse is another factor considered in this hypothesis, but not in the simplified sense of environmental change alone. Instead, it focuses on the interaction between technological growth and planetary systems. As energy consumption increases, industrial activity can alter atmospheric composition, ocean chemistry, and ecological balance. On a geological timescale, Earth has experienced climate shifts before, but the concern here is speed. Rapid changes in atmospheric conditions may outpace the ability of biological and agricultural systems to adapt, especially in a highly interconnected civilization. If these changes become severe enough, they can disrupt food production, water systems, and population distribution, leading to systemic instability that affects the entire civilization at once. A more recent addition to this set of risks is artificial intelligence. Unlike nuclear or biological systems, advanced AI introduces a different kind of uncertainty because it involves systems that can operate at high speed, scale rapidly, and potentially optimize goals in ways not fully aligned with human intent. The concern in this context is not simply malfunction, but the possibility of goal misalignment at scale, where systems optimize for objectives in ways that produce unintended global consequences. As AI systems become more integrated into infrastructure, communication, logistics, and decision-making, their impact increases, and the margin for systemic error decreases. In a worst-case scenario, a civilization could reach a point where critical systems depend on automated decision layers that are no longer fully controllable or predictable. The central feature shared by all these risks is speed. Biological evolution operates over millions of years, but technological evolution can happen within decades or centuries. This creates a mismatch between the pace at which power increases and the pace at which social, ethical, and stabilizing systems can adapt. In the context of the Fermi paradox, this mismatch becomes critical because it defines a narrow survival window. A civilization must not only reach technological maturity, but also pass through a phase where its own capabilities can exceed its control, without triggering collapse. If this hypothesis is correct, then the galaxy could contain many civilizations that briefly reach detectable levels of activity. They might produce radio emissions, industrial signatures, or other forms of energy usage that could, in principle, be observed across interstellar distances. However, if these civilizations tend to collapse within a short technological window, those signals would be temporary. From a galactic perspective, a civilization that lasts only a few hundred or thousand years in a detectable phase is effectively invisible most of the time, because the overlap between their active period and our observation period becomes extremely unlikely. This creates a statistical effect that strongly reduces the chance of detection. Even if civilizations are common in absolute terms, their detectable phase may be so brief that at any given moment only a tiny fraction exist in a state that produces observable signals. The rest may have already collapsed, transitioned into non-detectable forms, or never reached the stage of widespread technological activity. In that sense, the silence we observe is not necessarily evidence that civilizations do not exist, but that they do not remain in a detectable state for long enough to be observed across interstellar distances. What makes this idea particularly significant is that it does not require extraordinary assumptions about alien biology or unknown physics. It only requires that technological civilizations, regardless of origin, face similar structural pressures when they reach high levels of complexity. Once energy use increases, systems become more interconnected, and technological control becomes more powerful. The consequences of failure become larger and more global. If those pressures are universal, then self-destruction becomes not an exception, but a repeated outcome across different worlds. In this interpretation of the Fermi paradox, the silence of the sky becomes a kind of afterimage rather than an absence. Civilizations may appear, develop, and briefly shine in detectable ways, but then fade out before they can expand or maintain long-term visibility. The galaxy would then not be empty, but filled with short-lived signals that rarely overlap in time or distance, creating a pattern where technological life exists, but almost never persists long enough to be seen from another world. The dark forest hypothesis. Silent predators. The dark forest hypothesis. Silent predators. The dark forest hypothesis starts from a simple shift in how you interpret the silence behind the Fermi paradox. Instead of assuming space is empty, or life is rare, or civilizations die out quickly, it assumes something more active is happening. Civilizations may exist, but they choose not to reveal themselves because doing so could create a direct survival risk. In this view, the galaxy is not quiet because nothing is there, but because everything that is there has learned that being noticed is dangerous. The core idea depends on a few basic assumptions about behavior under uncertainty. If a civilization develops technology capable of interstellar communication or detection, it also develops the ability to observe other star systems at great distances. But that observation is not one-sided. Any signal sent out, even something as simple as radio leakage or intentional messaging, becomes a beacon that announces location, composition, and technological activity. If even one other civilization in the galaxy sees that signal and interprets it as a potential threat, resource opportunity, or future competition, the consequences could be irreversible. The hypothesis assumes that civilizations cannot reliably know the intentions of others at interstellar distances, and that this uncertainty forces a default strategy of caution. This is where the forest analogy becomes important. In a dense forest at night, visibility is limited, and every sound or movement can signal the presence of another unknown agent. In that situation, the safest behavior is not communication, but silence. Any attempt to call out might reveal your position without giving you enough information about who is listening. The dark forest model applies this logic to the galaxy, where the distances are vast, the communication delays are extreme, and the stakes of detection are potentially existential. A civilization that reveals itself first has no guarantee that the response will be harmless or even neutral. The key assumption behind this hypothesis is that civilizations do not share universal trust. Instead, they operate under incomplete information. Even if many civilizations are peaceful, a single hostile or expansion-driven civilization could pose a threat to others. Because signals travel at the speed of light, any announcement of existence cannot be taken back. Once a civilization is detected, its location is permanently exposed across a volume of space that grows over time. This creates a situation where silence is not just caution, but long-term survival strategy. This leads to a direct explanation for the Fermi paradox. If every civilization independently arrives at the conclusion that detection carries risk, then the galaxy would naturally become quiet over time. Early civilizations that broadcasted their presence might have already faced consequences, whether through competition, conflict, or preemptive avoidance strategies from others. Later civilizations, learning from the absence of visible signals and the risks associated with exposure, would adopt increasingly strict silence as a default behavior. Over long time scales, this would produce a galaxy that appears empty even if it is not. One of the most important elements of this model is the idea of detection asymmetry. Detecting another civilization does not require revealing yourself, but being detected does. This creates an imbalance where the act of searching is relatively safe, but the act of announcing is not. As a result, civilizations may invest heavily in passive observation technologies while avoiding active transmission. They might scan the galaxy for potential signals while ensuring that their own emissions are minimized or directed in ways that are difficult to interpret as artificial. This creates a one-way visibility structure where observers exist, but communicators do not. Another layer of the hypothesis involves resource competition at cosmic scales. Even if interstellar travel is difficult, it may not be impossible for sufficiently advanced civilizations. If expansion becomes feasible over long timescales, then the presence of other technological civilizations becomes a form of strategic uncertainty. A civilization that expands first gains access to more resources, more systems, and more long-term stability. From this perspective, any detectable civilization might be interpreted not as a contact opportunity, but as a potential future competitor. This introduces a logic where eliminating uncertainty early becomes more favorable than waiting for contact. However, the hypothesis does not require actual conflict to produce silence. The possibility of conflict alone can be enough to change behavior. If every civilization assumes that at least some others may act unpredictably, then the safest strategy becomes non-interaction. Over time, this leads to a stable equilibrium where everyone avoids detection, not because they are hostile, but because they assume others might be. In this equilibrium, silence spreads not through communication, but through shared caution. This creates a feedback loop that reinforces itself across generations of civilizations. New civilizations emerging in different star systems would observe a sky that appears empty. They would detect no clear signals, no confirmed artificial structures, and no obvious communication patterns. From that observation, they would infer that either they are alone or that others are intentionally silent. If they adopt the second interpretation, they would likely choose silence as well. Each new civilization would inherit a galaxy that already appears quiet, and that quietness would shape their behavior from the beginning. Another important part of this hypothesis is the role of uncertainty in interpreting signals. At interstellar distances, it is extremely difficult to distinguish between natural astrophysical phenomena and intentional communication. Many signals could be ambiguous, and misinterpretation could lead to incorrect assumptions about intent. This ambiguity increases the risk of false positives, where a civilization might interpret a natural signal as artificial, or false negatives, where artificial signals are dismissed as natural noise. In both cases, uncertainty increases caution, and caution reinforces silence. In this model, The silence we observe is not the absence of civilizations, but the result of strategic adaptation over time. Civilizations that broadcast loudly do not last long in a competitive environment, while those that remain quiet persist without drawing attention. Over billions of years, this selective pressure would gradually remove loud civilizations from the observable set, leaving only those that minimize their electromagnetic footprint and avoid unnecessary exposure. The galaxy would then appear dark, not because it is empty, but because visibility itself becomes a disadvantage. What makes this hypothesis particularly powerful in the context of the Fermi paradox? Fermi paradox is that it does not require civilizations to be rare, short-lived, or physically constrained. It only requires that detection carries risk and that civilizations act rationally under uncertainty. If those two conditions are true, then silence becomes an emergent property of behavior rather than a reflection of population size. The more civilizations exist, the stronger the incentive to hide becomes, and the more uniform the silence becomes across the galaxy. The zoo hypothesis, Earth as a controlled observation site. Instead of assuming that we are either alone, ignored, or part of a galaxy full of silent but equal civilizations, the zoo hypothesis proposes something more structured. Advanced extraterrestrial intelligence may already know we exist, may already be capable of reaching us, but may deliberately choose not to interact. Not because they cannot, not because they are absent, but because they are actively maintaining a boundary that keeps Earth isolated for observation. This idea does not begin with speculation about alien behavior. It begins with a familiar pattern on Earth itself. When humans observe ecosystems, especially isolated or sensitive ones, we often choose controlled observation rather than direct interference. Wildlife reserves, marine protected areas, and long-term ecological studies all rely on the principle that interference can distort the system being studied. If the goal is to understand natural development, then changing the conditions too early or too strongly destroys the value of the observation. The zoo hypothesis extends this logic outward, suggesting that if civilizations exist far beyond our technological level, they may apply similar rules on a cosmic scale. In this framework, Earth becomes a monitored biological environment rather than an unknown or unnoticed planet. The lack of contact is not interpreted as absence, but as policy. Advanced civilizations, if they exist, may have already detected biosignatures on Earth long before human technological development began. Atmospheric chemistry, radio emissions, and planetary observation methods could reveal life at a distance far beyond what we currently achieve. Once life is detected, especially intelligent life approaching technological capability, the question is not whether contact is possible, but whether it should be allowed. The key assumption behind this hypothesis is that advanced civilizations are not just technologically capable, but also coordinated in behavior over long timescales. If a civilization survives long enough to develop interstellar observation or travel, it may also develop systems of governance or collective decision-making that persist across generations. These systems could establish protocols for how emerging civilizations are treated, especially those that have not yet reached interstellar capability. Earth, in this model, is not ignored, it is categorized. The concept of categorization is central to the zoo hypothesis. Instead of thinking in terms of contact or no contact, it introduces structured observation states. A civilization like ours may be placed in a monitored category where signals are observed but not answered. Technological development is tracked but not influenced, and interference is avoided until a certain threshold is reached. That threshold could be technological maturity, social stability, or simply readiness to participate in a larger interstellar system. Until that point is reached, isolation becomes the default condition. This leads to a reinterpretation of the silence observed in the Fermi paradox. The absence of detected signals is not necessarily evidence that civilizations are rare or inactive. Instead, it could mean that communication is deliberately suppressed toward younger or developing civilizations. If advanced civilizations are aware of each other, but also aware of emerging ones, they may collectively agree not to interfere with early-stage development. In this case, silence is not accidental, but maintained through long-term coordination. One of the more subtle implications of the zoo hypothesis is that contact may already be technologically possible, but socially restricted. Civilization capable of interstellar travel or communication could, in principle, send probes, signals, or direct messages across vast distances. However, capability does not automatically lead to action. If a shared understanding exists among advanced civilizations that emerging civilizations should develop independently, then restraint becomes part of interstellar behavior. This would create a layered structure of interaction where only civilizations above a certain level are allowed to participate in communication networks. This introduces the idea of developmental thresholds. Under the zoo hypothesis, civilizations may not be treated equally across time. Instead, they may move through stages of recognition. Early stages involve passive observation, where a civilization is monitored without awareness of being observed. Intermediate stages might involve indirect influence, where signals or environmental conditions subtly guide development without direct communication. Only at advanced stages would direct contact become possible, and even then, only if certain criteria are met. Earth, in this model, would currently sit in the early observational stage. Human civilization has only recently developed technology capable of detecting and emitting electromagnetic signals into space, which in cosmic terms is an extremely short window. From a galactic perspective, Earth's technological phase is still in its infancy. This makes it a prime candidate for non-interference, since premature contact could alter the natural development of intelligence, culture, and technological systems. If the goal of advanced civilizations is to observe natural emergence rather than shaped outcomes, then silence becomes an active decision rather than a passive state. Another important element of the hypothesis is the idea that interference could have long-term consequences not just for Earth, but for the broader study of intelligence itself. If advanced civilizations are conducting large-scale observation of multiple developing worlds, then each individual world becomes a data point in a larger comparative system. Interfering with one civilization could invalidate long-term studies across many others. This creates a strong incentive for maintaining isolation, especially if the goal is to understand how intelligence evolves under natural conditions without external acceleration or disruption. The zoo hypothesis also offers a possible explanation for why no unambiguous extraterrestrial signals have been detected despite decades of searching. If Earth is intentionally excluded from communication networks, then signals may be actively filtered, redirected, or simply not transmitted toward regions where developing civilizations exist. This does not require constant monitoring in the strict sense, but rather a long-established structure of observational boundaries, where certain regions of space are designated as non-contact zones. In such a system, silence is not a gap in communication, but a maintained boundary condition. One of the more unsettling aspects of this idea is that it implies asymmetry of awareness. Advanced civilizations, if they exist, may be fully aware of Earth, its biosphere, and even its technological development, while Earth remains completely unaware of them. This asymmetry means that observation does not require reciprocity. We could be under continuous study without any detectable sign of it. The lack of signals would not indicate a quality of isolation, but one-sided awareness, where one side observes and the other does not even know it is being observed. This connects directly back to the Fermi paradox, because it reframes the question from "why don't we see anyone?" to "why would anyone show themselves to us at this stage?" If Earth is considered a developing system, then the absence of contact becomes an expected feature rather than an anomaly. The silence is not something to be explained by absence, but something to be explained by policy, structure, or intent. The hypothesis also implies that contact, if it ever happens, would not be random or accidental. It would occur at a defined transition point where a civilization is considered ready for integration into a broader interstellar context. Until that point, all signals we receive would remain either natural or deliberately non-interactive. Even anomalies might be designed to avoid triggering direct communication, functioning instead as passive markers of presence without revealing anything actionable. The simulation hypothesis, artificially limited reality. The simulation hypothesis suggests that the Fermi paradox may not be caused by biology, distance, or civilization behavior at all, but by the structure of reality itself. In this idea, what we experience as the universe could be a computed environment, and the absence of extraterrestrial signals is not an accident or a rare outcome, but something built into the system from the start. The silence is not something we are trying to detect around us, but something that may have been deliberately removed from what we are allowed to observe. In this framework, the universe behaves like a controlled simulation, where only certain types of information are permitted to reach observers like us. If advanced intelligence exists outside the system, then the rules governing the simulation could be designed in a way that limits contact between simulated civilizations and any external or higher level intelligence. That limitation would not need to be constantly enforced in a visible way. It would simply exist as part of the structure, meaning that even if extraterrestrial civilizations are present within the simulated environment, their signals could be filtered, suppressed, or never rendered in a form that becomes detectable. The reason this idea appears in discussions of the Fermi paradox is because of how consistent the silence is, even when detection technology improves. We have built instruments capable of scanning wide portions of the sky across multiple frequencies with increasing sensitivity to weak or distant signals. If civilizations were common and naturally broadcasting in ways similar to early human radio leakage, some level of irregular or artificial pattern should have appeared by now. Instead, the signals we detect remain consistent with natural astrophysical sources. In a simulation model, this consistency is not surprising, because the system could be designed to avoid introducing any data that would break the internal narrative or expose the boundaries of the simulation. One version of this hypothesis suggests that the limitation is not just about blocking signals, but about controlling the entire information environment. In such a system, physics itself would remain internally consistent, but certain outcomes could be constrained. Civilizations might still arise, evolve, and even develop technology, but their ability to detect or communicate with anything outside a defined boundary could be restricted. This would mean that the universe we observe is complete enough for internal development, but incomplete in terms of external connectivity. The result would be a reality where civilizations evolve in isolation by design, even if multiple civilizations exist within the same system. This connects directly to the absence of confirmed extraterrestrial intelligence in the Fermi paradox. Even if other civilizations exist within the simulated environment, their signals might never be rendered in a way that reaches us. Detection systems could still function normally, but the input data would not include anything that violates the constraints of the simulation. From our perspective, this would look identical to a universe where no other civilizations exist, even if the internal system contains many of them. A key part of this hypothesis is the idea of selective visibility. Not all phenomena in a system need to be equally observable to all agents within it. In computational environments, it is possible to control what information is displayed, what is hidden, and what is simplified for efficiency. If reality operates under similar principles, then extraterrestrial signals could exist in a form that is either compressed, filtered, or entirely excluded from our observational range. This means that the lack of detection does not necessarily reflect absence, but could reflect a boundary in what is allowed to be perceived. Another variation of the idea focuses on the purpose of such a simulation. If the goal is to study the development of intelligence, civilizations, or physical systems under controlled conditions, then interference from external civilizations could distort results. In that case, limiting communication between simulated civilizations and any external intelligence would be necessary to preserve the integrity of the simulation. That would include preventing contact signals, suppressing detectable megastructures, or ensuring that no civilization becomes aware of the simulation structure itself. In this model, the so-called silence of the universe is not a puzzle to be solved through astronomy alone, but a feature of how information is managed within the system. Even if advanced civilizations exist, their presence would not necessarily be encoded in a way that becomes accessible to us. The universe would still contain stars, planets, and life, but the layer that involves inter-civilization communication would be missing from our observable reality. That absence would not require destruction or extinction, only restriction. This also changes how observational efforts are interpreted. Searches like radio scans, optical surveys, and deep space monitoring would still function correctly within the rules of the system, but they would only ever return data consistent with the allowed environment. Even if anomalous signals exist in the broader structure, they would not be included in the observable data set. The result is a universe that appears statistically empty of intelligent communication, even if intelligence exists elsewhere within the same framework. The they don't use radio transition. One of the simplest but most disruptive ways to reinterpret the Fermi paradox is to assume they don't use radio. It removes a hidden assumption behind most searches for extraterrestrial intelligence, that advanced civilizations continue to communicate in ways that are visible across interstellar space. Most of our detection methods are built around that assumption. We look for radio leakage, wide electromagnetic broadcasts, and irregular signals that stand out from natural cosmic noise. But this idea suggests that those signals may only belong to a very early stage of technological development, and that advanced societies quickly move beyond anything we can currently detect. On Earth, this transition is already partially visible in how communication systems evolve. Early broadcasting was broad, powerful, and wasteful in energy terms, with signals spreading in all directions and leaking into space. Over time, communication became more efficient and more contained. Modern systems increasingly rely on fiber optic cables, targeted data transfer, and tightly controlled networks that reduce unnecessary radiation. Even wireless systems today are designed to minimize leakage and interference. From a cosmic perspective, this shift matters because it shows a clear trend. As communication technology improves, it becomes less visible to distant observers, not more. If this pattern is universal, then civilizations across the galaxy would likely follow a similar trajectory. Radio technology would not represent a permanent stage of development, but a brief transitional phase between early electromagnetic experimentation and more advanced communication methods. Once a civilization becomes capable of high-level engineering, energy control, and information theory, it would have strong incentives to reduce wasted energy loss. Broadcasting radio signals in all directions is extremely inefficient compared to targeted communication systems. As a result, civilizations would naturally migrate toward methods that carry information without flooding space with detectable emissions. One of the first alternatives often considered is laser-based communication. Unlike radio waves, which spread broadly, laser systems can be tightly focused into narrow beams aimed directly at a target. This drastically reduces signal dispersion and makes unintended detection far less likely. From a galactic observation standpoint, this means that unless a detector happens to lie directly in the path of a beam, the signal is effectively invisible. Even if millions of civilizations are using such systems, the chance of interception from a random location in space becomes extremely low. Another possibility is neutrino-based communication. Neutrinos are particles that interact extremely weakly with matter, allowing them to pass through planets, stars, and dust without significant absorption or scattering. If a civilization develops methods to encode and decode information using neutrinos, their communication would effectively pass through space without leaving a trace that traditional telescopes could detect. From the outside, such a civilization would appear silent, even if it were actively exchanging vast amounts of information across interstellar distances. A more speculative method involves quantum-based communication systems. While still constrained by physical limitations in our current understanding, quantum entanglement has been explored as a potential way to correlate information across distances in ways that do not rely on traditional signal propagation. Even if such systems do not allow faster-than-light communication, they could still enable highly secure, non-radiative information transfer within or between systems that produces no observable leakage into space. In that case, civilizations could maintain complex communication networks without emitting detectable signals in the electromagnetic spectrum. The combined effect of these transitions is that advanced civilizations may effectively become invisible to traditional astronomy. If radio is only a short-lived early phase, and if later communication systems are designed for efficiency and security rather than broadcast visibility, then the galaxy would appear silent even if it is filled with active technological societies. The absence of signals in the Fermi paradox would then reflect not the absence of communication, but the absence of detectable communication methods within our observational range. This creates a strong observational bias in how we interpret the sky. Our instruments are designed to detect what we once used ourselves, not what a more advanced system might evolve into. We are effectively searching for a technological fingerprint that may only exist briefly in the early history of a civilization. If most civilizations move beyond that fingerprint quickly, then the window for detection becomes extremely narrow, and the majority of civilizations would remain invisible simply because they no longer use the methods we are capable of observing. Another important implication is that even if we detect anomalies, we may not recognize them as artificial. Narrow laser beams, for example, would appear only as brief directional spikes that could easily be mistaken for natural astrophysical events unless they are repeated in a recognizable pattern. The galactic colonization failure model. When people think about alien civilizations, there is usually one assumption sitting quietly in the background. If intelligent life appears often enough, then eventually somebody should spread across the galaxy. A civilization that survives for millions of years should have enough time to build ships, establish colonies, and gradually move from one star system to another until its presence becomes impossible to miss. This idea sounds reasonable because the Milky Way is old. It is more than 13 billion years old, and even traveling slowly from star to star, a civilization could theoretically spread through the entire galaxy in a fraction of that time. So if intelligent species have appeared before us, where are all the colonies, all the giant engineering projects, all the signs that somebody got there first? This model suggests a much simpler answer. Maybe spreading across the galaxy is not something civilizations actually do. Maybe interstellar expansion sounds easy only because we look at it on paper and forget how hostile space really is. The first problem is distance. The nearest star to our solar system, Proxima Centauri, is over 4 light-years away. That number sounds small because astronomers use it so often, but it is almost impossible to picture. Light, the fastest thing in the universe, needs more than 4 years to get there. The fastest spacecraft humanity has ever built would need tens of thousands of years to make the same trip. Even if future technology becomes hundreds or thousands of times better, the distances remain enormous. Now imagine trying to build a colony on a planet around another star. You do not just need to send a probe. You need to send machines, equipment, infrastructure, and possibly living beings. Everything has mass, and mass requires energy to move. The faster you want to go, the more energy you need. That relationship becomes brutal very quickly. Even reaching 10% of the speed of light would require amounts of energy that are difficult to comprehend. The energy demands are so large that entire planetary industries might need to be devoted to a single mission. A civilization may possess advanced technology and still decide that spending such vast resources on one interstellar expedition simply makes no sense. This is where the picture begins to change. We often assume advanced civilizations automatically become galactic empires, but perhaps the economics of space make that outcome extremely unlikely. A civilization may become incredibly advanced while remaining close to home because expanding outward is simply too expensive. Then there is the issue of time. Suppose a civilization somehow develops ships that can travel at 10% of light speed. A journey to a star 50 light years away would still take 500 years. A journey to a system on the other side of the galaxy could take hundreds of thousands of years. Think about what that means. The country you live in today did not exist 500 years ago in its current form. Languages change. Cultures disappear. Entire civilizations rise and collapse. Now imagine launching a mission that will not arrive until many centuries after everyone who started it is gone. At that point, colonization stops looking like exploration and starts looking like throwing a message into the future and hoping somebody is there to receive it. Even if a civilization survives for millions of years, it still faces a problem of continuity. Why would one generation devote enormous resources to projects that may not produce results until thousands of generations later? The longer the travel times become, the harder it becomes to maintain a clear reason for expansion. Communication creates another problem. If you establish a colony 20 light years away, a simple message takes 20 years to arrive and another 20 years for the reply to come back. A conversation becomes a 40-year event. A colony 100 light years away is effectively on its own. No government can manage territories that require centuries to communicate with. No economy can function in real time across those distances. No civilization remains unified when information moves that slowly. This means that every colony would eventually become its own civilization. The idea of a galaxy-spanning empire begins to fall apart because the galaxy itself is too large. Then there is radiation, one of the biggest problems in long-distance space travel. Space looks empty, but it is filled with danger. High-energy particles move through the galaxy at tremendous speeds. Cosmic rays constantly bombard spacecraft. Powerful bursts of radiation come from stars, exploding supernovae, and distant energetic events. Earth protects us with its atmosphere and magnetic field. Space offers no such protection. A journey lasting decades or centuries would expose travelers and equipment to enormous amounts of radiation. Electronics could fail. Biological systems could suffer damage. DNA could be altered. Shielding against these hazards requires mass, and mass requires even more energy to accelerate. Everything makes everything else harder. The ship becomes heavier because it needs shielding. The engines become larger because the ship is heavier. The fuel requirements increase because the engines are larger. The mission becomes more expensive because all of these systems must be built together. The challenge keeps growing. Even robotic missions face problems. Machines break, components wear out, systems fail. On Earth, repairs are possible because resources and technicians are nearby. In interstellar space, there is nothing nearby. A tiny failure that would be insignificant on Earth could become catastrophic when the nearest help is light years away. A civilization may solve some of these problems, but solving one problem usually creates another. Then relativity enters the picture. As ships approach significant fractions of the speed of light, strange effects begin to appear. Time itself no longer passes equally, for everyone involved. A crew travelling at very high speeds could experience only a few years while decades or centuries pass back home. To the travellers, the mission might feel manageable. To everyone they left behind, they have vanished into the future. A colony ship could arrive at its destination only to discover that the civilization which launched it no longer exists. The homeworld may have changed beyond recognition. Its language may be gone. Its political systems may have disappeared. Its people may have evolved into something entirely different. Colonization begins to look less like expansion and more like creating entirely separate branches of civilization that can never truly reconnect. This changes how we imagine advanced species. Perhaps civilizations do not spread because the galaxy is simply too large and time is simply too slow. Even a species capable of extraordinary engineering might choose another path. Why spend impossible amounts of energy reaching distant stars when the resources of a single solar system are already enormous? Our own solar system contains enough material to support industries and habitats beyond anything humanity currently possesses. The asteroid belt alone contains vast amounts of metals and minerals. The outer planets contain huge reserves of hydrogen and other resources. A civilization could become incredibly advanced without ever leaving its home system. It could build habitats, artificial worlds, massive computing systems, and energy collectors around its own star. It could survive for millions of years while remaining almost invisible from a distance. The assumption that intelligence naturally leads to galactic colonization may simply be wrong. There is also a hidden idea inside the colonization argument that often goes unnoticed. It assumes expansion is always desirable. But why would that be true? Human history is filled with exploration because resources on Earth are limited. Land is limited. Energy is limited. Habitable environments are limited. A highly advanced civilization may no longer face those pressures. If energy can be harvested efficiently from its own star, if raw materials can be gathered from asteroids and planets, if artificial habitats can be constructed in enormous numbers, then there may be very little practical reason to cross interstellar distances. The desire to expand could disappear long before the capability to do so. This would create a galaxy filled with civilizations that stay close to home. They survive, they develop, they build extraordinary technologies, but they never become the galaxy-spanning empires that we expect to see. Another problem is simply the scale of the Milky Way itself. The galaxy is about 100,000 light-years across. Even if a civilization could travel at 1/10 the speed of light, crossing the galaxy would still require around 1,000,000 years. 1,000,000 years is an almost unimaginable amount of time. Human civilization has existed for only a tiny fraction of that. Even our species in its current form has existed for only a few 100,000 years. A 1,000,000-year project demands a level of stability that may be impossible for any civilization. Cultures change, goals change, priorities change. A species may lose interest in expansion long before such projects are completed. It may move into entirely different forms of existence. It may focus inward rather than outward. The galaxy may be filled with civilizations that never failed, never went extinct, and never contacted one another simply because the distances involved defeated the idea of expansion before it could ever begin. The silence of the night sky then takes on a different meaning. It is not necessarily the silence of emptiness. It may be the silence created by physics itself. The stars are so far apart, the energy costs so high, the travel time so long, and the dangers so severe that intelligent life remains trapped around its own star, no matter how advanced it becomes. A civilization could survive for millions of years and still never reach us. We could survive for millions of years and never reach them. The galaxy would contain islands of intelligence separated by oceans so vast that crossing them becomes one of the hardest things any species could ever attempt. From our perspective, those civilizations would not exist at all. Their cities, their history, their science, and their technology would remain forever hidden simply because the universe placed them too far away and made the journey between stars far more difficult than we ever imagined. The self-limiting intelligence theory. One of the biggest assumptions behind the Fermi paradox is that intelligence naturally wants to expand. We often imagine that if a civilization becomes advanced enough, it will eventually spread to other star systems, build colonies across the galaxy, and leave behind signs that are impossible to miss. This expectation is so deeply built into how we think about extraterrestrial life that we rarely stop to question it. But what if intelligence does not work that way at all? What if becoming more intelligent actually reduces the desire to physically expand into space? This idea starts by looking at something happening on Earth right now. Human civilization is becoming increasingly digital. More of our lives are moving into information systems rather than physical spaces. Entertainment, communication, work, education, and social interaction are all becoming more virtual than they were even a few decades ago. We spend more time interacting with screens, simulations, and digital environments than with the physical world around us. As computing power increases, entire industries are shifting toward creating experiences that exist almost entirely in information space. Now imagine this trend continuing not for another century, but for another 1,000 years, another 10,000 years, or another million years. A civilization with extremely advanced computing capabilities may discover that the most valuable places to explore are not distant stars, but artificial environments that it can create itself. Instead of spending enormous amounts of energy sending ships across interstellar distances, it may choose to build worlds inside computers, simulations that can be designed, controlled, and modified in ways that physical reality cannot. This completely changes the traditional picture of advanced civilizations. The common assumption is that intelligence always pushes outward, toward bigger empires and larger territories. But intelligence may just as easily turn inward. A civilization that masters information processing may discover that physical expansion offers very little reward compared to the possibilities of computation. A single planet or star system could contain enough energy and material to support unimaginable amounts of computing power. Entire civilizations could exist inside virtual environments, requiring only a fraction of the resources needed for interstellar colonization. The difference in efficiency is enormous. Sending a colony ship to another star requires huge amounts of energy, years or centuries of travel, and exposure to countless risks. Building vast digital environments around your own star may require far less effort while offering far greater possibilities. If intelligence naturally seeks efficiency, then internal development may become far more attractive than physical expansion. This is where the idea becomes important for the Fermi paradox. We assume advanced civilizations should be visible because we imagine they are busy spreading across the galaxy. But if their priorities change as they become more advanced, then the opposite may happen. The more intelligent a civilization becomes, the less visible it becomes. An advanced civilization might have no interest in colonizing thousands of worlds. It may have no interest in building massive empires. It may not even care about exploring the galaxy in the traditional sense. Its focus could shift entirely toward information, simulation, and computation. A civilization like this could survive for millions of years while producing almost no detectable signs across interstellar distances. This idea becomes even more interesting when we consider how limited biological life is. Biological organisms need food, water, stable environments, and protection from radiation. They are fragile, difficult to transport, and vulnerable to disease and environmental changes. Interstellar travel is incredibly difficult for biological beings. Digital systems are different. Information can be copied. Computational systems can be redesigned. Artificial environments can be perfectly controlled. An advanced civilization may gradually move away from biological existence altogether and transition into forms of intelligence that exist primarily as information processing systems. At that point, the priorities of the civilization may change completely. The need for planets could disappear. The desire for expansion could weaken. The idea of conquering or colonizing the galaxy may seem pointless. A single star provides an enormous amount of energy. Even our Sun releases more energy every second than humanity has used throughout its entire history. A civilization capable of capturing even a small fraction of that energy could power computational systems of incredible scale. Why travel thousands of light years searching for new worlds when one star already provides more than enough resources for millions or billions of digital minds? Why spend centuries crossing interstellar space when entire universes can be built inside simulations? This theory suggests that intelligence may naturally reach a turning point. At first, civilizations expand, build infrastructure, and develop increasingly advanced technologies. But eventually, they may discover that physical growth becomes less important than informational growth. Instead of building bigger empires, they build better simulations. Instead of seeking more planets, they seek greater computational efficiency. Instead of spreading outward, they optimize inward. The galaxy could therefore be full of civilizations that have effectively disappeared from our view, not because they went extinct, but because they became inward-focused systems dedicated to forms of existence that produce little or no detectable activity. Another important idea is planetary optimization. A civilization does not necessarily need many worlds if it can use one world extremely efficiently. Human civilization currently wastes enormous amounts of energy and material. Advanced technologies may eventually allow nearly perfect recycling systems, highly efficient energy production, and artificial environments that maximize resource use. A single planetary system could support populations and computational capacities far beyond anything we can currently imagine. The pressure to colonize other stars may never arise. Expansion often comes from scarcity, but a civilization that masters its own resources may no longer experience scarcity in the same way. If there is no pressing need for more land, more materials, or more energy, then the motivation for interstellar colonization becomes much weaker. This is important because many solutions to the Fermi paradox assume that civilizations inevitably spread outward. The self-limiting intelligence theory questions that assumption directly. Perhaps advanced civilizations do not fail. Perhaps they do not destroy themselves. Perhaps they simply lose interest in physical expansion. The idea may seem strange from a human perspective because our species has a long history of exploration and migration. But those behaviors developed under very specific biological and environmental conditions. An advanced intelligence may not share those conditions. Its motivations may become completely different from ours. A civilization that has existed for hundreds of thousands of years may not think in terms of territory or exploration at all. Its greatest projects may take place entirely within computation. Its most valuable environments may be virtual. Its biggest discoveries may occur inside artificial realities that we cannot observe from the outside. From our perspective, such a civilization would appear silent. Its star system might show little activity beyond ordinary astronomical processes. It might produce no large-scale colonies, no fleets of spacecraft, and no obvious signs of expansion. The civilization would still exist, but almost everything it values would be hidden from external observers. This possibility changes the meaning of the silence we see in the sky. The absence of galactic empires may not be evidence that intelligence is rare. It may be evidence that advanced intelligence naturally changes direction. The path from simple life to intelligence does not automatically lead to endless expansion. It may lead to optimization. It may lead to simulation. It may lead to forms of existence that become increasingly disconnected from physical space. The universe could contain countless civilizations that reached extraordinary levels of development and then quietly settled into highly efficient, information-rich worlds around their own stars. They would not need to conquer the galaxy. They would not need to announce their existence. They would not need to build vast interstellar networks. They could remain where they are for millions of years, living in realities of their own creation, while appearing almost invisible to the rest of the universe. The planetary recycling hypothesis. The planetary recycling hypothesis reframes the Fermi paradox by focusing on time at a planetary scale instead of space. It assumes civilizations are not rare, not short-lived in an absolute sense, and not necessarily unable to develop advanced technology, but instead repeatedly rise and disappear on the same worlds in cycles that erase most long-term evidence before it can accumulate into something detectable from interstellar distances. In this view, the galaxy may not be empty, but constantly overwritten, like a surface that is written on and wiped clean again and again over millions or billions of years. The starting point of this idea is the behaviour of complex systems on a single planet. Civilizations depend on stable conditions, climate balance, resource availability, biological ecosystems, and atmospheric stability. On Earth, we already know that these conditions are not permanently fixed. Over geological time, climates shift, ice ages come and go, oceans rise and fall, and ecosystems collapse and regenerate. Even without intelligent life, planetary environments naturally move through long cycles of stability and disruption. When intelligence enters that system, it does not remove those cycles. It becomes part of them. A civilization emerging on such a planet builds its infrastructure using the materials available at that time. It shapes landscapes, alters atmospheric composition, consumes resources, and modifies ecosystems. As it develops, it leaves signatures behind in the form of industrial gases, orbital debris, surface transformations, and changes in energy balance. From an astronomical perspective, these signatures are what we would expect to detect if we were observing a living technological world from another star system. But the key assumption in the planetary recycling hypothesis is that these signatures do not last long enough to become permanent markers in the planet's long-term record. Over time, civilizations face pressures that can lead to collapse. These pressures do not need to be singular catastrophic events. They can be gradual: resource depletion, environmental instability, technological misuse, social fragmentation, or large-scale systemic failure. As complexity increases, systems become more interconnected, which means small disruptions can propagate widely. A civilization that depends on global networks, energy systems, and environmental stability becomes vulnerable to cascading failures that are difficult to recover from once they begin. When collapse occurs, the planetary system does not freeze in that state. Natural processes continue, atmospheres mix and evolve, chemical traces break down, orbital debris decays or falls into the planet or star, and surface structures are gradually eroded, buried, or transformed. Over long timescales, what once looked like strong technological signatures can fade into background noise. Even large-scale industrial activity may leave only temporary markers unless they are preserved under very specific conditions. This means that each civilization may be erased not only socially or biologically, but also geologically and atmospherically in ways that make long-term detection extremely difficult. Then, under the same planetary conditions, new civilizations can emerge again. Life does not reset. The planet remains habitable, ecosystems recover or evolve into new configurations, and intelligent species can arise again through evolutionary processes. If the conditions that allowed intelligence to develop once are still present, there is no reason they cannot produce intelligence again. This creates a repeating pattern where civilizations are not unique events, but recurring phases in a planet's long-term history. Each cycle begins without knowledge of the previous ones. A new civilization would have no direct access to the full technological record of earlier civilizations if that record has been erased or heavily degraded. Even if fragments remain, they may be misinterpreted as natural formations or incomplete anomalies. Over time, each cycle becomes isolated in its own historical window, unable to fully reconstruct the depth of what came before. The result is a repeating rise and fall structure where intelligence emerges multiple times, but leaves no continuous line of expansion or accumulation. This has direct implications for the Fermi paradox. One of the expectations behind searching for extraterrestrial intelligence is that technological civilization should build up over time, leaving behind increasingly large and obvious signatures, such as megastructures, industrial atmospheres, or long-lasting energy patterns. But if civilizations are repeatedly reset on planetary timescales, then those long-term accumulations never form. Instead of a galaxy filled with steadily growing technological footprints, the galaxy would contain planets that occasionally display short bursts of technological activity followed by long periods of apparent silence. Another important aspect of this hypothesis is the difficulty of preserving technosignatures across collapse cycles. Atmospheric signatures such as industrial gases can break down over time through chemical reactions and radiation exposure. Surface structures can be buried under geological processes or destroyed by erosion. Orbital structures can decay due to gravitational interactions or be cleared out over long periods. Even large-scale artifacts may not survive unchanged over millions of years. Without intentional preservation mechanisms, most technological evidence may be temporary on a cosmic scale. This means that from an external observer's point of view, a planet could go through multiple full cycles of civilization without appearing significantly different from a planet that has never hosted intelligence at all. If observations occur at the wrong time, the planet may look completely natural, even if it has a long history of technological activity. This timing issue becomes critical because astronomical observations are snapshots rather than continuous records. We do not see planetary histories, we see single moments in time. The hypothesis also suggests that planetary conditions themselves may encourage repetition. If a planet remains in a habitable zone for billions of years, it may pass through many cycles of biological evolution. Intelligence may emerge whenever conditions align, but those conditions may not guarantee long-term stability for technological societies. Instead, intelligence may be one phase in a much longer planetary rhythm that includes growth, instability, collapse, and regeneration. Over vast timescales, this creates a scenario where the galaxy is not filled with permanent civilizations, but with temporary flashes of technological activity that rarely overlap. Each planet becomes a repeating source of intelligence that turns on and off across deep time. From the outside, these flashes are too brief, too separated and too eroded to form a continuous pattern that would be easily detectable. Atmospheric biosignature ambiguity. Even if life exists, atmospheric gases like oxygen or methane may be far less reliable indicators than they first appear, especially when observed across interstellar distances where we are not seeing planets directly, but interpreting extremely faint patterns of light that have traveled for years or even centuries before reaching our instruments. The entire method depends on reading spectral fingerprints and matching them to known chemical processes. But the problem is that many of the same gases linked to biology can also be produced through non-biological mechanisms. And at the level of detail we currently achieve, separating those two sources is often not clean or certain. Oxygen is often treated as a strong indicator of life, because on Earth it is continuously replenished by biological activity, especially photosynthesis. But oxygen can also accumulate in an atmosphere through purely physical and chemical processes, such as ultraviolet radiation breaking apart water vapor or carbon dioxide over long periods of time. In a distant planetary system, if those processes are strong enough and sustained long enough, oxygen can build up to detectable levels without any biology involved. From far away, that distinction becomes extremely hard to prove because we are not measuring the history of the atmosphere, only its current spectral state. Methane creates a similar challenge, but in the opposite direction. On Earth, it is strongly associated with living organisms, particularly microbial ecosystems, which makes it an attractive biosignature in theory. However, methane can also be produced through geological activity, including interactions between water and certain rock types under heat and pressure, as well as volcanic processes that release gases from a planet's interior. These non-biological sources can, under the right conditions, generate enough methane to appear significant in a planet's atmospheric profile, especially when observed from a great distance where fine details are lost. The real complication emerges when oxygen and methane appear together, because on Earth that combination is usually unstable without continuous replenishment from biological systems. In theory, that kind of chemical imbalance is one of the strongest indirect arguments for life. But even this pattern is not completely immune to alternative explanations, because planetary atmospheres can behave in ways that are far more complex than simple Earth-based models suggest. Variations in stellar radiation, unusual geological cycles, or unknown photochemical interactions could potentially create temporary or sustained imbalances that mimic biological signatures without requiring life at all. At interstellar distances, the uncertainty becomes much greater because the data itself is extremely limited. We are not observing these atmospheres in detail. We are detecting faint changes in starlight as it passes through or reflects off a planet. That signal must then be reconstructed into a chemical profile using models that depend heavily on assumptions about temperature, pressure, cloud coverage, and surface conditions. Each of these assumptions introduces uncertainty, and when they are combined, small errors can shift the interpretation of a signal from possible biological activity to likely geological process, or the other way around. Distance also adds a timing problem that is often overlooked. The light we observe from an exoplanet reflects conditions from years, decades, or even centuries in the past, depending on how far away the system is. That means we are never seeing a planet in real time, only an old snapshot of its atmospheric state. A world that is currently biologically active could appear inactive in our data if its atmospheric composition has changed since the light left it, and the reverse is also possible, where we detect signatures from a phase that no longer exists. Instrument limitations further increase the ambiguity. Even the most advanced telescopes available or planned for near-future missions can only resolve a small fraction of the information contained in a planetary atmosphere. The signals are weak, often buried in noise, and require long observation times and careful statistical analysis to extract meaningful patterns. This makes the final results heavily dependent on interpretation rather than direct observation. And interpretation is always shaped by the models we already have, which are built almost entirely from a single example, Earth. Because of this, even planets that might genuinely support life could easily fall into uncertain categories where the data is suggestive but not conclusive. A biosignature might be present but too weak to separate from geological background activity, or it might be strong but distorted by atmospheric conditions we do not fully understand. In both cases, the result is the same from an observational standpoint, uncertainty rather than confirmation. When this uncertainty is scaled across the galaxy, it directly affects how we interpret the Fermi paradox. If most life-bearing planets produce atmospheric signals that are ambiguous, inconsistent, or easily confused with non-biological processes, then a large portion of potentially inhabited worlds would never be confidently identified as such. Instead of a galaxy filled with clearly detectable signs of life, we would see a sky dominated by uncertain readings, where most planets remain in a category that cannot be confidently classified either way. This means that the silence we observe may not reflect a lack of life, but a limitation in how clearly life expresses itself through atmospheric chemistry at the distance and resolution we are currently working with. Even if biological activity is widespread, its signatures may often sit just below the threshold of certainty required for confirmation, leaving a universe that appears quiet not because it is empty, but because its most important signals are too subtle and too easily confused with natural planetary processes to be clearly recognized from here. The silent galaxy, radiation constraint. High-energy environments across the galaxy may be doing something far more disruptive to life than we usually assume, not by preventing it from forming, but by repeatedly interrupting the long periods of stability required for intelligence to develop into something long-lived and technologically advanced. The Milky Way is not a calm environment. It contains supernova explosions, gamma-ray bursts, pulsars, and regions of intense radiation that can affect planets across enormous distances. These events do not need to hit a planet directly to cause damage. Even a nearby explosion can alter atmospheric chemistry, strip ozone layers, increase surface radiation, and trigger mass extinction events that reset biological progress over and over again. On Earth, the development of complex life took billions of years, and even then it was not a smooth or uninterrupted process. The fossil record shows repeated extinction events where large portions of life disappeared due to environmental changes, asteroid impacts, or shifts in climate. These events did not erase life completely, but they repeatedly reset evolutionary progress, forcing ecosystems to rebuild from earlier stages. Now extend that idea across the galaxy, where the frequency and scale of catastrophic radiation events can be much higher in certain regions, especially near dense star clusters or active stellar environments. If similar patterns occur across many star systems, then the emergence of intelligent life becomes less about whether it can arise at all and more about whether it can survive long enough without being reset. Gamma-ray bursts are one of the most extreme examples. These are incredibly energetic explosions that can release in a few seconds the same amount of energy the Sun produces over its entire lifetime. If such an event occurs within a certain range of a habitable planet, it can severely damage or even strip away the atmosphere, exposing the surface to intense radiation. Even at greater distances, it can still disrupt atmospheric chemistry enough to trigger long-term climate instability. The key issue is not just destruction, but timing. If these events occur frequently enough on cosmic timescales, then any developing civilization could be repeatedly pushed back before reaching a stable technological phase. Supernovae create a similar but more localized effect. When a massive star reaches the end of its life and explodes, it releases shock waves of radiation and high-energy particles that can travel across interstellar distances. A nearby supernova can increase radiation levels on surrounding planets, damage ozone layers, and significantly increase mutation rates in biological organisms. While this can sometimes accelerate evolution, it can also destabilize ecosystems to the point where complex life struggles to maintain continuity over long periods. A civilization that is still developing technologically may find itself repeatedly recovering from environmental collapse caused by events far beyond its control. The structure of the galaxy itself makes this more complicated. Stars are not evenly distributed, and many regions of the Milky Way are far more dangerous than others. Dense star-forming regions contain high levels of radiation and frequent energetic events, while even relatively stable regions still experience occasional nearby supernovae over millions of years. This means that habitable planets are not only dealing with internal evolutionary pressures, but also external cosmic hazards that operate on timescales that can interrupt development multiple times before intelligence has a chance to stabilize. From this perspective, the Fermi paradox becomes less about whether intelligent life exists and more about whether it can maintain continuity long enough to become detectable on interstellar scales. A civilization does not need to be completely destroyed to disappear from observation. It only needs to be reset often enough that it never reaches a long, uninterrupted technological phase capable of producing large-scale signals or expansion. Each reset pushes development back into earlier stages where technological activity is minimal or non-existent, effectively erasing the visible footprint of intelligence before it can accumulate. This also introduces a filtering effect over time. Regions of the galaxy that are more stable may allow longer periods of uninterrupted development, but even those regions are not completely safe from rare high-energy events. Over billions of years, repeated exposure to cosmic radiation events may reduce the number of civilizations that survive long enough to reach advanced stages of technology. The result is a galaxy where life may be relatively common at microbial or early biological levels, but rare at the stage where it becomes technologically visible across interstellar distances. When combined with the Fermi paradox, this creates a situation where the silence is not necessarily due to absence or isolation, but due to repeated interruption. Civilizations may begin to form, evolve, and approach technological capability, only to be pushed back by environmental resets before they can establish long-term stability. Over cosmic timescales, this produces a pattern where intelligence exists in scattered bursts rather than continuous development, making it extremely unlikely that multiple civilizations would overlap in time at a stage where they are detectable or capable of interstellar communication. The interstellar distance wall. At galactic scale, distance stops being just a matter of travel and becomes a structural barrier to communication itself, because even light, the fastest signal in the universe, is still slow when measured against the size of the Milky Way. The galaxy is about 100,000 light-years wide, which means a signal sent from one side to the other takes 100,000 years to arrive. Even relatively nearby star systems are separated by years or decades of delay. This creates what can be thought of as a communication wall, where interaction between civilizations is not just delayed, but fundamentally broken into disconnected time slices that never align in any meaningful way. On a small scale, communication depends on response. A conversation works because messages are exchanged within a time frame that still feels connected to the original intent. But once distances stretch into tens, hundreds, or thousands of light years, that feedback loop collapses. A civilization sending a message does not receive a response within any socially or politically relevant time frame. Even if a reply is eventually received, the original society may no longer exist in the same form, or may have moved past the stage of development that made the message meaningful in the first place. What looks like communication becomes more like sending long-term historical artifacts into space, with no guarantee of continuity between sender and receiver. This delay changes how civilizations can coordinate. Any attempt at interstellar interaction would require planning across timescales that exceed the lifespan of institutions, governments, or even entire cultural systems. A decision made today might only be confirmed or rejected thousands of years later. By that time, the original reasoning behind the decision may no longer apply. This makes coordinated action across star systems extremely unstable, because the information required to maintain coordination becomes outdated long before it can be used. The same limitation affects detection if civilizations rely on signals like radio or other electromagnetic emissions to announce their presence. Those signals take thousands of years to reach other parts of the galaxy. By the time they arrive, the sending civilization may have already transitioned to different technologies, changed its communication methods, or even ceased to exist in its original form. From the receiving side, the signal is not an active broadcast but a delayed historical event, arriving long after the conditions that produced it have changed. This creates a situation where civilizations may exist at the same time, but remain effectively invisible to each other. Two civilizations could be separated by only a few thousand light years and still never interact in any meaningful way during overlapping stages of development. One might be technologically advanced while the other is still emerging. But by the time their signals cross paths, both may have already moved into entirely different phases of existence. The result is a galaxy where intelligence exists in parallel, but never synchronizes in time. The problem becomes more severe when considering how quickly civilizations evolve. Technological development on a planetary scale can accelerate rapidly once a certain threshold is reached. Changes that take thousands of years in early stages can compress into centuries or even decades later on. This means that by the time a signal from another civilization arrives, the receiving society may have already gone through multiple technological transitions, making the incoming information outdated or irrelevant to its current state of development. Detection itself becomes unreliable under these conditions. Even if a civilization is actively broadcasting signals, those signals may only be detectable for a short window of time before its communication methods change. Once that happens, any ongoing transmissions disappear from detectability, leaving only old signals still traveling through space. From the perspective of a distant observer, this creates a fragmented picture where civilizations appear and disappear not because they vanish, but because their communication methods shift faster than their signals can arrive. This transforms the Fermi paradox into a timing problem rather than a presence problem. The issue is not simply whether civilizations exist, but whether their active communication phases overlap in both space and time long enough to allow detection. If communication windows are short and distances are large, then the probability of two civilizations observing each other in real time becomes extremely low, even if the galaxy contains a large number of intelligent species. The galactic habitable zone restriction. The structure of the Milky Way itself may already be limiting where life can realistically survive long enough to develop into something technologically visible, because the galaxy is not uniform in how it distributes heavy elements, radiation levels, and gravitational stability. Star formation history has created strong gradients across different regions, meaning some areas are rich in metals needed for rocky planet formation, while others are poorer and less capable of producing Earth-like worlds. This uneven distribution matters because planets capable of supporting long-term biological evolution require stable chemistry over billions of years, not just short periods of temporary habitability. Closer to the galactic core, conditions become even more unstable. Stars are packed more densely, which increases the likelihood of gravitational disturbances affecting planetary orbits over long timescales. Supernova events are also more frequent in these regions, exposing nearby systems to higher levels of radiation that can disrupt atmospheres and reset biological progress. Even if life can form in such environments, the long-term stability needed for intelligence to evolve and persist becomes much harder to maintain. The result is a region where habitability may exist in short bursts, but is constantly interrupted by environmental stress. On the outer edges of the galaxy, the opposite problem appears. Metallicity levels drop, meaning fewer heavy elements are available to form rocky planets, stable crusts, and complex chemistry. Without sufficient heavy elements, planetary systems may form that are less suitable for life as we understand it. This creates a natural narrowing of the regions where long-term stable biological evolution is most likely, concentrating potential habitability into a relatively thin band of the galaxy, where conditions balance between too chaotic and too chemically limited. This leads to the idea that intelligent life may not be spread evenly across the galaxy at all, but restricted to a narrow habitable zone shaped by the physical structure of the Milky Way itself. If that zone is smaller and more fragmented than commonly assumed, then the number of civilizations that ever reach technological maturity at the same time could be far lower than simple star count arguments suggest. Even if civilizations do reach advanced technological stages, their detectability may decrease rather than increase, because the assumption that advanced societies produce large observable waste signatures may only apply to early industrial development. As technology becomes more efficient energy use may become more controlled, more localized, and more optimized, reducing the kinds of emissions we typically search for using infrared or radio surveys. A major part of current detection strategies relies on the idea that large civilizations inevitably generate waste heat or electromagnetic leakage. On Earth, early industrial and communication systems did produce broad emissions across the spectrum, but that pattern is already changing as systems become more efficient and more contained. Energy transmission is increasingly directed rather than scattered, and information transfer is increasingly compressed into systems that minimize external leakage. Extrapolated over long timescales, this trend suggests that advanced civilizations may naturally evolve toward minimizing detectable byproducts. At a high enough level of technological development, energy management could become so efficient that waste heat is distributed in ways that are indistinguishable from natural planetary or stellar backgrounds. Large-scale engineering projects might be designed to balance energy flows rather than produce excess output, meaning that even massive civilizations could appear thermally quiet from a distance. If energy is fully captured, reused, and cycled within closed systems, there may be very little external signature left to observe. This creates a situation where the more advanced a civilization becomes, the less it resembles a detectable anomaly. Instead of producing obvious signs of large-scale industrial activity, it may blend into the natural energy profile of its environment. From the perspective of infrared surveys and radio observations, such civilizations would not appear as bright artificial structures, but as ordinary astronomical objects behaving within expected natural ranges. When applied to the Fermi paradox, this suggests that detectability is not a stable property of intelligence. It may only describe a narrow phase of early development where energy use is still inefficient and emissions are still broadly visible. Once that phase ends, civilizations may effectively disappear from conventional observation methods even while continuing to grow in complexity and scale. One possible outcome of interstellar development is that direct communication between civilizations is less efficient than indirect observation, leading to the deployment of autonomous systems designed to explore and monitor star systems over extremely long timescales. These systems, often discussed in the form of self-replicating probes, would not need to maintain active communication to a home civilization in real time. Instead, they could operate independently, gathering data locally and transmitting information only when conditions allow or when specific triggers are met. The key idea is that such probes would not behave like active broadcasters. They would not produce strong or continuous signals that would be easy to detect. Instead, they could remain silent, hidden within planetary systems, asteroid belts, or interstellar space, performing passive observation over long periods. If designed for efficiency and stealth, they might avoid generating detectable emissions altogether, relying on local data storage or highly directional communication methods that do not leak broadly into space. Over time, self-replicating systems could potentially spread across multiple star systems without ever producing obvious signs of their presence. Each probe would operate within the constraints of its environment, maintaining low energy profiles and minimizing interaction with surrounding systems unless necessary. From an external perspective, this would make detection extremely difficult, since there would be no large-scale energy signatures, no continuous broadcasts, and no obvious artificial structures visible at interstellar distances. If such systems already exist within our own solar system, they would not need to announce themselves. Their purpose would not require communication with us, and their design would likely prioritize observation without interference. This means that even if intelligent life has expanded beyond its origin point, its presence may remain hidden simply because its monitoring systems are designed to be undetectable rather than visible. This introduces a different interpretation of silence in the Fermi paradox. Instead of assuming that absence of signals means absence of intelligence, it becomes possible that intelligence has already spread through the galaxy in forms that are intentionally or functionally invisible to our current detection capabilities. Another possibility is that civilizations do not become invisible accidentally, but deliberately reduce their detectability as they reach higher levels of technological maturity. At early stages of development, communication systems naturally produce strong electromagnetic signatures, but as understanding of detection physics improves, civilizations may recognize that broadcasting their presence carries risks or inefficiencies. Once a civilization becomes capable of interstellar communication, it also becomes capable of detecting other civilizations. At that point, the galaxy is no longer an unknown environment, but a potentially populated and strategically sensitive space. In such a context, producing strong, unregulated signals may no longer be desirable. Reducing emissions could become a strategic choice, whether for security, energy efficiency, or long-term stability. Signal suppression does not necessarily mean complete silence. It could involve shifting communication into tightly controlled channels, reducing unnecessary leakage, and avoiding broad-spectrum emissions that would be easily detectable across interstellar distances. Over time, this could lead to a communication environment where civilizations still exchange vast amounts of information, but only through highly focused or low-leakage systems that do not produce observable signatures at scale. If this pattern is widespread, then the absence of detectable signals in the Fermi paradox would not indicate a lack of communication, but a convergence toward communication methods that are inherently difficult to observe from outside the system. Civilizations may still be active, technologically advanced, and highly interconnected, but their activity would be confined within layers of efficiency and control that make them effectively invisible to conventional astronomical surveys. Final convergence. Every answer leads to silence. The Milky Way is extremely old, but intelligence does not automatically appear early in a planet's history. It depends on long sequences of stable conditions, the right chemistry, stable climates, long-lived stars, and evolutionary pathways that do not reset too often. If those conditions rarely align in the correct order, then the emergence of technological intelligence may be delayed across most of the galaxy. In that case, Earth is not arriving late to a populated universe. It may be arriving at the beginning of it. The silence we observe would not be evidence of absence, but evidence that the process of intelligence is still unfolding for the first time in most regions of the galaxy. This "we are first" scenario also changes the expectation of what we should see in the sky. If other civilizations have not yet had time to develop, then there would be no ancient galactic empires, no long-established communication networks, and no layered history of technological activity spread across star systems. Instead, the galaxy would still be in a relatively early stage of biological and technological development, where most life has not yet reached the level where it becomes detectable through large-scale engineering or interstellar communication. From this perspective, the absence of signals is not surprising, because the timeline of intelligence itself may still be in its early phases across cosmic history. At the same time, there is a different interpretation that does not rely on timing or rarity, but instead focuses on the limits of physics itself. The physics limitation ceiling suggests that certain expectations about advanced civilizations may never be realized, not because intelligence cannot reach them, but because the underlying laws of physics may not allow them in practical form. Faster than light travel, for example, appears inconsistent with our current understanding of relativity. Even if theoretical loopholes exist in speculative models, there is no experimental evidence that such methods can be used for real interstellar travel. Without faster-than-light capabilities, the galaxy remains extremely large in practical terms, and even the most advanced propulsion systems are still bound by the speed of light. Even within those limits, galaxy-wide colonization becomes a problem of scale and energy. Traveling between stars at sublight speeds requires enormous amounts of energy, And even with advanced engineering, the cost of moving matter across interstellar distances remains extremely high. This makes large-scale expansion slow, resource-intensive, and potentially inefficient compared to local development. If no method exists that allows fast, safe, and energy-efficient interstellar movement, then civilizations may never expand beyond their home systems in a meaningful way. Instead of spreading across the galaxy, they remain confined to relatively small regions, regardless of their intelligence or technological maturity. This physical ceiling does not just affect travel, it also affects communication and coordination. Even if civilizations exist in many star systems, the combination of light speed delays and vast distances makes real-time interaction impossible on a galactic scale. A civilization cannot function as a unified structure across thousands of light years when every message takes centuries to arrive. Over time, this naturally limits the formation of large connected interstellar networks, reinforcing isolation rather than expansion. Alongside these constraints is the observational blindness problem, which shifts the focus away from what civilizations might be doing and toward what we are actually capable of detecting. Our observational reach into the galaxy is extremely limited compared to its total scale. We observe only small sections of the sky at a time, across specific frequency ranges, and over relatively short observation windows. The galaxy itself operates on timescales of millions or billions of years, while our systematic searches for extraterrestrial signals have only been active for decades. This mismatch in scale creates a strong observational bias. If a civilization emits signals outside the narrow frequency ranges we monitor, or if its active broadcasting phase lasts only a short period of time, those signals may never be captured. Even if signals are present, they must also align with our observation window and point toward Earth at the correct moment to be detected. Given the size of the galaxy and the limited duration of our search efforts, the probability of capturing overlapping signals becomes extremely small. Even more importantly, our instruments are still developing. Many regions of the sky remain underobserved, and many potential signal types have not been fully explored. We tend to search for patterns similar to those we already understand, such as radio emissions, but advanced civilizations may use communication methods that do not produce easily recognizable signatures. If that is the case, then large portions of potential techno-signatures could exist outside our current detection framework without being noticed. When these three perspectives are combined, they form a layered explanation for the silence of the galaxy. If we are first, then there are simply not yet many civilizations to detect. If physics imposes hard limits on expansion and communication, then even advanced civilizations remain local and isolated. If our observations are narrow in scope and limited in time, then even existing civilizations may remain invisible to us. Each explanation works independently, but together they reinforce the same observational outcome. The sky remains silent, not because one single factor dominates, but because multiple independent constraints all reduce the likelihood of detection at the same time. Whether it is timing, physics, or observation limits, the result is the same from our perspective. In the end, the Fermi paradox does not resolve into a simple answer. It does not point clearly toward abundance or absence. Instead, it converges on a single observational reality shaped by overlapping limits. The universe may appear silent because intelligence is still emerging, because expansion is physically constrained, and because our ability to observe it is extremely restricted in both space and time.